use any one of the two. Assumption for both equations, meaning that both equations are valid, is that the transmission line has been assumed lossless. If the transmission line cannot be assumed lossless, then clearly there's going to be loss of the power as it propagates through the line, and we'll address this thing just in the next topic. Now, let me look at very quickly some very common special cases. Essentially, we're going to look at a few cases where the ZG is known, and even though they're special cases, they occur in practice very, very often. So the first and probably most common case is that the line is actually matched to my source. So ZG, in other words, is equal to Z naught. That is very common when you basically buy a power supply. When you buy, for example, an RF power supply, the manufacturer has made sure that the internal impedance of ZG is actually equal to Z naught. That means that when you buy a power supply, you'll find that most often than not, your ZG is equal to 50 ohms. So when that happens, your gamma G that we just discussed is going to be equal to 0. That means that your source is matched to the line. And there are some useful equations that come out of this. So the V naught plus will become very simple. It's essentially half of Vg with this exponential. And then all of the equations that we have discussed before will basically become greatly simplified. So the first equation I discussed before was giving you this PL. I also discussed this PL equation here. And finally, this equation is also valid. And again, you can see the details of that in my notes. Now, there is another case where now not the transmission line is matched to the source, what we all try to achieve in real life, which is we're trying to make sure that my transmission line, my source rather, with an internal impedance of ZG is not just matched to the line, but actually is matched to the Z-in complex conjugate. This is the conjugate matching case. This is the case that, assuming the transmission line is lossless, would guarantee that all of the available power from the source will actually hit the load. So I want to clearly emphasize here that this is the case that we normally try to get in real life. We try to get essentially the source to get all of its power to the load. Make sure that this is happening. ZG has to be equal to Z-in complex conjugate. Now, sometimes in real life, you will see people that apply a different condition, which means that ZG is equal to Z naught and ZL is equal to Z naught. And I would really encourage you to think about under which case this essentially gives you the maximum power transfer that we are talking about here. It will give you maximum power transfer if you have real impedances, but if you have complex impedances, it's much safer to do what I'm basically showing here. Now, if ZG is equal to Z-in complex conjugate, then PL is equal to the equation right here. And you will often see that in books as being called the maximum available power. In other words, this number that you will see in the box here is the maximum power that the source can ever provide to your load, and it's really up to you to make sure that you can collect this power by making sure that conjugate matching is satisfied.